All right. Okay. So the last remaining thing to prove is we are going to investigate what happens to circles which are, a generic circle under inversion. Okay, that's what we want to know. All right, so let's go back. So what is the construction? So we are going to take a generic circle. First of all, we're going to take a circle of inversion. Okay, C. I think the circle of inversion is not that important actually. It will just distract. So let's in fact not even care about the circle so much. We'll just draw the center of inversion. Okay, the center of the circle of inversion, that's what we'll draw. And there is a circle here, okay, there is a circle here. But you should not focus on it, okay, because it's not very helpful. It will just distract you. So let's draw a circle which we want to invert, okay. Notice that the circle, the way I'm thinking about it, it is neither orthogonal, it's not even cutting in the first place. I've drawn such an example. And it certainly is not passing through the center of inversion. Okay, we are taking now a circle, a new case. All right. So here is Coxeter's wonderful idea to do this. So he wants to actually understand how does the circle invert to. His strategy is amazing. This is going to give you the answer to what that circle really is using dilation. Okay, the inverted circle will actually give you the formula for. So the idea is the following: take an arbitrary point P on the circle, and I will tell you how to locate the inverse of this point P by the following method. What you do is you join this P, O and P, and you extend. Join OP and extend. Okay. So I think maybe I should write it here. Join, let P belong to omega. Extend OP to cut omega again at Q. So this point where it cuts again is Q. A line and a circle can cut at most at 2 points. I'm assuming this point P is not the tangent. I mean, if it is, then Q is again P actually. In this case, in the drawing that I have drawn, Q is not P. Okay. So let extend OP to cut omega again at Q. And when you cut, now what you do is the following. First of all, notice that OP into OQ is constant. It is just the power of the point O with respect to omega. Okay, so let P equal OP into OQ, which is simply the power of the point P with respect to omega. Let K be the radius of the circle of inversion. Okay, that's our usual notation. This K is the radius of the circle of inversion. Then consider the dilation, and this is really the genius. So consider the dilation. D about O with the factor k square by P. Okay. Consider dilating the plane with center O and radius k square by P. From whatever discussion we had under dilation, this circle will dilate to another circle. Let's draw that circle. Okay. So this circle omega under dilation goes to a new circle omega bar. Okay. Under dilation with that factor k square by P. And when it goes, we know that the center will go to the center. Okay. Let's say this is the center and this is the center C bar. And we know that this point Q will go to some point Q bar. I don't care about P bar for a minute. So this goes to Q bar, Q goes to Q bar. And we know that, QC and Q bar C bar are parallel, are supposed to be parallel. Okay. We know all this. Now, what is the relation between OP and OQ? Let's understand. So, since we have dilated with k square by P, then OQ by OQ by OQ, by definition of dilation, is just k square by P. But remember, P is OP into OQ. Now see, something very interesting happens. This Q, OQ and this OQ cancels. And if you rearrange, you will see OP into OQ bar is k square. So OP into OQ bar is the radius square. So by definition of inversion, Q bar must be inverse of P. So therefore, Q bar is the inverse of P under the circle of inversion. I mean, we don't know what to call it now. I mean, I guess I already called C the center. So let's call it gamma or something. So, okay. And if you don't like this, you can simply call it P dash. Okay, P dash is our usual notation. So it turns out this point Q bar that we obtained completely by dilation, by the way. What you did is you just started with the point O, you joined it to P, you extended it to meet at another point Q, and then you looked at the dilation of Q about O with that factor K square by P. It went and fell here Q bar. That Q bar is the inverse of P. Okay. However, it might look convoluted and complicated really to get that inverse because you have to dilate and do something. But remember, it gave you the full circle for free. What now happens is that no matter how you move P, you can use this procedure. And always you will dilate it with omega. I mean, this omega bar is fixed. It doesn't really depend upon P. Notice the construction. This omega bar was really the image under the dilation. It was basically the image of omega under that dilation. And that dilation depends only on K and P. Now, K is basically it's independent of P. And the small p is also independent of this point P. Because the small p is actually the power of the point O with respect to omega. It doesn't depend upon P and Q at all. So this omega actually goes to omega bar and it's independent of P. Therefore, this omega bar, which is indeed the circle, this omega bar is basically the inverse of omega. Okay, so we have IC of omega equal to omega bar, which is amazing. Okay, so you actually located even the center if you want. If you want to do formulas now, you can use this dilation and you can do the calculations. Okay, so this proves, by the way, that if you take a circle not passing through O, okay, under inversion, it will go to another circle not passing through O. Now, it turns out, by the way, this proof really works for orthogonal circles as well. If the circle was orthogonal to begin with, if the circle was orthogonal to the circle of inversion, it will turn out that this circle will just overlap with the circle itself. Okay, there won't be anything. Basically, what will happen is that this Q bar that you were constructing will just overlap with the. If you start with P here and you wanted to get Q bar, it will turn out Q bar will become Q. Okay, and what is the reason Q bar will become Q? The only way Q bar will become Q under dilation is if K square by P is equal to 1. And if K square by P is equal to 1, then it's the statement that OP into OQ is K square. But OP into OQ is K square is the statement, if you remember, that Q is the inverse of P, and so this circle is essentially orthogonal. Okay, you can go back and check our orthogonality discussion for this. So indeed, even for orthogonal circles, this entire proof works. All right, so this is the end of the basic properties of inversion. In fact, using just these basic properties, we can do many inversion problems. In the next set, we will give you standard inversion configurations, which are generally useful in problem solving in Olympiads and so on. Okay, so see you guys next.